hopefully. Yes. Okay, so I'm recording too, so looks like we're good to go. So yeah, for the, like, I guess for my plan for today is to kind of just like maybe do the sample midterm, and then also we can just do the like some theory questions, right? So that's also something we could try to work on. Maybe we start with the theory questions just to have something to talk about. And luckily got a nice message to help organize the theory questions. So yeah, let's try answering some of these. These are just some someone sent this to me very gratefully. And let's try to answer some of these things together. Things that could be theory questions on the exam, involved in true or false, short answer, this kind of stuff. So 5 big issues in SOC and like IC design as well. So in IC design, the first thing is like time. So this means like the clock speed, as well as the clock speed. So that's the first thing. And if anybody, by the way, please unmute and say stuff in the chat if you want to add anything. Anyway, so time, and then let's see if I remember them all. Time. I know power consumption is one of them. I don't know if power consumption is the next thing, but power consumption is one of them. So that's pretty self-explanatory what power consumption is. And then there's also reliability, which is about my understanding is like it's about like how the IC was manufactured, like defects. And then we also have reconfigurability or configurability. I think it's just configurability. Configurability, which is just like how it's like kind of like a balance. I'm just kind of giving you some key words here that I think he would give marks for. So balance between manufacturing standards and just like flexibility, I guess. There's one more because it's 5 big issues, and let's see if I can remember the 5th big issue. It is something area. I think it's area. Chip area. There we go. So it's like the literal like physical size. Physical IC size. So I definitely see this as this is definitely, it could be a theory question. So that's pretty good. These 2 things are about, I got a comment, so let's see what the message is. Cost, one of them. I think that's related to chip area. It's related to kind of all of these, right? Like if you want the chip area, if you want the clock speed to be faster, you need like higher end components. Power consumption to be lower, you need higher end components and stuff like that, or cost will increase. So I feel like cost is kind of associated with all of them. I could be wrong. I don't know. Please someone correct, but that's my opinion. The next 2 here are about JPEG stuff. I don't know if there's going to be JPEG stuff on the test. I don't know. But anyways, let's just answer these quickly. The why DCT over DFT. So discrete cosine transform, discrete Fourier transform. Basically, the way I remember it, like the only really key thing that I remember is that DCT is purely real. And then the DFT has like imaginary components. So yeah, I don't know. Is there any addition to this one? If there is, please mention. But otherwise, I don't think there's anything else to add here. And then the 4 stages of JPEG compression. Again, I don't know if this is going to be like, I don't know if he's actually going to, did he indicate in lecture? Did he say like that this is going to be covered on the exam, or did he say this is just like that lecture 4 was just for the lab, or did he not indicate that at all? Did he not mention it? Anybody know? Does anybody attend the lectures? I don't. He just said lecture 1 to 5. Okay, there you go. Never specified. Okay, well, it's possible. So then the 4 stages. Let's just do this here. Q2. The 4 stages are, first of all, we have let me just remember here. 3, 4. So the last one I remember is Huffman encoding. And then I think it's Zigzag is one of these two. I don't know. The first one is just like the DCT. Or is there like pre-processing? Does that count as one? I don't think that counts as one.
DCT? It counts as one, buddy.
Oh, it does count as one. Pre-processing?
You gotta 8x8 pixel blocks.
Yeah.
And then DCT.
And then DCT, and then Zigzag.
Yep.
Yeah, okay. So Zigzag, and there we go. So like, yeah, I break it into 8x8 blocks, DCT, Zigzag, Huffman encoding. There you go. That is that. Yeah, quantization kind of goes with this. Plus quantization. Quantization. If I can spell it, that'd be nice. There you go. Quantization. Okay. Question 4. Anybody stop me if you have anything to add or anything like that. Question 4. Why choose accelerators? Well, accelerators, have better performance. They can do things faster. They can do things with less power. And they can do things in parallel with the processor. Those are all good things that improve performance and throughput. Can't really think of anything else. Oh, increases scalability of the system. I don't know. Anybody have anything else to add about why to use accelerators? So, just in general, just like better performance. Better performance. In terms of in terms of time, in terms of power, in terms of like money, probably. I don't know. Time to develop as well. And then, someone's saying accelerators are also on the SoC itself. Coprocessors are external. Are coprocessors external? Like, necessarily? They're external? I haven't heard that before, but maybe. I just know that a coprocessor, the difference is like coprocessors actually take in and interpret instructions. Accelerators don't interpret instructions. They have a task, and they do that task. Coprocessors have multiple tasks they can complete based on the instructions given to them. Again, if I'm wrong or if anyone has anything to add, please, add. But yeah, coprocessors actually like execute instructions. That's why it's a processor. But I think they're also on the chip. They're also on the SoC. Anyways, so there's that. So let's keep moving. Question 5. Hardware, software partitioning. So this is why don't I type? It's a little easier to type. So why don't I type this? We could... why don't I save this just in case something happens? COE838 midterm review. Hardware software partitioning. This is the partitioning, for lack of a better word, partitioning of the tasks into partitioning of the tasks into functional units, which can be hardware or software based. I don't know. Anything else to add to this? Let me see if there's definitely more words you can say here. Let me see on my tablet here. So what am I answering? I'm answering hardware software partitioning. yeah, so which functionality should be implemented as hardware and which should be implemented as software. And then I guess, yeah, we can talk about like some of the challenges here. So the things that we often, talk about in terms of hardware software partitioning is like the granularity. So granularity is like a feature or a parameter in how you do your partitioning. So you could have coarse grain approaches. A coarse grain approach means that you assign full functional blocks to hardware or software, whereas a fine grain approach means you just work with like simple operations. Okay, so that's like addition, subtraction, or whatever. Anyways, the simple operations. So, and you assign those to either hardware or software or stuff like that, right? So it's like, do you really want to get into details of like how the computer does every little thing in hardware or software, or do you just want to say, well, if you're doing this general thing, then do that in hardware, or this general thing, do it in software. So that's the difference between coarse grain and fine grain approach there. Yeah, I think that's everything. So let's just keep moving. Question 6. 4 principal phases of co-synthesis. I don't know. Co-synthesis. 4 principal phases of co-synthesis. I would just have to make up something if I was asked something on the test. Let's look at the slides, I guess. I don't know. What are the 4 principal phases of co-synthesis? Yes, Tree, you can talk. You don't have to raise your hand. Thank you for raising your hand, though.
If I remember correctly, it's partitioning. Then you got, I think, pipelining. And
Pipelining?
then yeah.
Okay.
I don't know which one comes first, assignment or allocation. Let's see. Allocation comes first, and then assignment.
Allocation, and then assignment. So what does this all mean? Okay, partitioning, I get. What are we're finding the 4 principal stages of synthesis? Yeah, co-synthesis. Co-synthesis. Okay, so partitioning, fine. We assign different tasks to different like hardware software units. Pipelining means like deciding like the size of the pipeline.
No, it's like choosing like which time that a unit would start doing its stuff.
Oh, so why are you calling that pipelining? Isn't that like scheduling?
It's also called like scheduling, if I recall.
Yeah. Okay. So pipelining / scheduling.
Yeah.
Scheduling makes sense. Yeah, like start and end times. Start plus end times. Yeah, okay. Plus end times. Allocation? I don't know what does allocation mean?
So it's memory serves like determining like which processing element. The abbreviation for that is PE.
Yeah.
Determine the processing element on when will it occur? Like when will it occur?
Isn't that scheduling?
When will like of the of like the computation like of a block.
Let me see.
Check. I think that's lecture 3.
Yeah. Yeah. Someone's in the chat here. Lecture 3, slide 16. Slide 16. Here. Okay. So partitioning is dividing the functionality of a specific system into units of computation. Scheduling or pipelining is task start timing. Okay. Allocation, determining the processing elements on which the computations occur. Oh, okay. So like partitioning is just deciding what should be done in hardware and in software. Allocation means, okay, so the hardware ones, what are the actual like, or it doesn't, maybe not just the hardware ones, but like, what are the well, I'm imagining just the hardware ones. Like, what are the actual things that are going to be running the hardware instructions? I guess. Determining the processing elements on which computations occur. Okay. Task mapping, choosing particular components for the allocation units. Like, all of this just means the same thing to me in my mind. Like scheduling and partitioning, sure, but then like these last two just mean partitioning to me. Choosing particular component types for the allocated units. Like, what's the difference between component type, unit of computation, and processing element? They all kind of mean the same thing to me. I guess processing element maybe is a hardware thing, but not even necessarily. I don't think it has to be a hardware thing. Yeah, I don't know. But yeah, so that's that. Well, this is the answer to the 4 principal phases of co-synthesis. Partitioning, scheduling, pipelining, allocation. Oops. And assignment. So I'll just put that here. To answer question 6. Okay. Let's kind of like go through the next bits kind of fast because I do kind of want to do some of the math questions. So system C features. There's a lot of features. We will have the card. The only system C question we'll have the coding one. I feel like they'll also ask like what are the different types of processes. So you have like methods, threads, and C threads. And my understanding of the difference between those three is that okay, so C threads are with a clock. So they're clock triggered. Threads are processes which are how do I explain this? Threads are okay, I gotta open the slides. I forget the exact defining differences here. Actually, I can just open this little thing here. So methods are executed and return immediately. Threads can be suspended and reactivated. C threads are like threads, but are activated by clock pulses. So methods are execute and return immediately, whereas threads can be suspended and reactivated, and are probably mostly like an infinite loop, I'm assuming. So you could probably add that in. Okay. 4 co-design elements of embedded systems. Not sure. Let's skip that for now. 3 types of IP cores. Okay, this I definitely see as being a question that he could put on. I would definitely hope. Oh, someone commented here. He could also ask for like what SC event is. Yeah, so like notify and wait. Yeah, these are like the concurrency control things that we have. Notify and wait. Yeah, he could also ask about that for sure. But I assume that's going to be just kind of like a part of a true and false question or something like that. Anyways, so types of IP cores. We have hard IP cores, we have soft IP cores, and we have firm IP cores. Hard IP cores are where so first of all, an IP core is like a reusable piece of hardware or just processing element, I guess. Does it have to be hardware? I don't know, but I feel like it does. And anyway, so the IP core, hard IP cores have like predefined hardware of how they work. Soft IP cores are just functionally defined. They just define their function. And then the hardware still has to be like synthesized. And then the Firm IP cores are where some of it is synthesized, but some of it is just functionally defined. Here, someone's put in the chat here. IP cores are reusable hardware or software components. They can be classified as hard IP cores, physical layout, soft IP cores, functional descriptions, or firm IP cores, balanced performance and flexibility. The only thing is like firm IP cores, so that means like, I guess that means some of it. Some of it is already predefined in hardware, and then some of it is just functionally defined. I guess. I don't know. All of this is kind of wishy-washy, but yeah. Anyways, so ASIC versus SoC. So they're very similar, but they're not the same thing. I mean, I think the difference is that ASICs, SoCs also incorporate software elements, right? They have like operating systems and firmware built into it. I don't think ASICs have that. But also that's just like a more cohesive device than SoC. But I think specifically it's the firmware. It's like the software thing. Anybody have a comment about this one? Like the difference between ASICs and SoC? My opinion is just the software thing. And then what does SoC consist of? Well, a lot of things, right? Computational units, intermodule communication networks, already like the memory is already in there. The computational, the accelerators are in there. The operating system is in there. Memory, I already said. I/O is in there. Analog circuits, that's an important thing as well. Yep, analog circuits are in there. There we go. Okay, so why don't we start doing like the question on the sample? Because I feel like it'd be nice to just try some of the numerical ones. But good discussion. Good discussion. So yeah, let's see here. You can do the task one. I feel like doing the area one, because I feel like the area one is confusing. And also, I don't have all the time, so I do got to go. We have 1 more hour, so I do just want to make sure we get this. So let's do the area one, and let's see if I can do everything properly. Hopefully that sounds good to everybody. So you are required to develop blah 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 something. Consider a wafer yield of 98%. So we know that our yield is 98%. I'll start just writing things down here. So yield equals 98%. A defect density, so that's rho D of 0.1. I spelled yield wrong, didn't I? Yield. That's how you spell yield? That is how you spell yield, yeah. My bad. So now 0.1 per square centimeter. Okay, we're going to mention this in a second. The target feature size is at the 65 nanometer technology node. I have no idea what all those words mean, but I think F equals 65 nanometers is what is trying to be communicated to me there, which means our lambda is 65 over 2 nanometers. All right, which is, just don't want to make a mistake, 32.5 nanometers. Okay, but we might not need that. I'm just, just finding information here. Okay, so we know all these areas here, right? We know that this takes 300A, 150A, 185A, all this stuff, right? What we'd like to find how much area we have in total, usable area we have in total, and then subtract all this stuff and make sure that this fits in to here. And like put a number here to kind of top it off for this S2. Yeah, let's finish reading the question. Assume 11% chip area for die costs, 12% for overhead integration for connecting. Generate an architecture and floor plan. So he said no floor plan. And don't even know what that means, generate an architecture. I mean, we're not drawing the interconnections of things, so I don't know. Anyways, show all calculations and steps undergone to implement your design. Specify all component areas and final capacity. So yeah, specify all component areas means finish filling in the table. And the final capacity, actual and practical, of the SRAM L2 cache your system may support. So the first thing is we need to figure out how much area we have, right? So there's kind of two ways that, I mean, I forget which way is what, but okay, there's two formulas that involve A, and it's very confusing. So we have this formula, which is yield equals e to the negative rho dA. And we know everything here, so we could solve for A, but I think this A is the number of, this A is the number of chips. I could be wrong with this. Let me verify with what I have here. So let me verify here. Da, da, da. So this A is, no, this is just the area. This is just the area. This is just the total area that we have. Okay, so we can rearrange this, right? Because this is 0.98 equals e to the negative 0.1a, and so you can rearrange this. So this is going to be, take the ln of both sides, ln 0.98 over negative 0.1 is equal to a, and then you type all this in. Let's see what we get when you just type it in. 0.98 over negative 0.1, and you get 0.202, and what unit is this in? Well, rho d, right, was in centimeters squared, so this is going to be in centimeters squared. Okay, so we have A now. We have the total area. This is how many centimeters squared we have. Okay. Now, 11% and 12% are used for stuff that we can't use. So in total, that means 23% is unusable. Right? So that means that our actual area, A, prime, A usable, is going to be 1 minus 0.23 times this A, right? So this is going to be 77, 0.77 times 0.202. So times 0.202. So this is 0.15554 centimeters squared. So that's our actual usable area. Now, we need to figure out how many A's. Now, this is a different A, okay? This area A is a different A than this A. This is like a predefined unit, and it takes 300 of those, and this takes 150 of those, and this takes 185 of those. And so we need to figure out how many of those A's we have in total. So I'm going to call that like AC, like A count, like we're counting how many A's. Turns out that A count is 1 over F squared. Okay, so we can do 1 over 65 nanometers squared. Okay, and so this is going to be what unit is this going to be in? This is going to be in. Let me just see here quickly. Oh yeah. Okay. Okay, you'll see what unit this is going to be in a second. So it's going to be just typing this into your calculator: 1 over 65 squared. Right. This means I get 0.0153846 per nanometer squared. What this means is that's how many I can fit. Every nanometer squared, I can fit that many A's. This unit A here. But I know it in centimeters squared, so I either got to convert the centimeter squared into nanometers squared, or I need to convert the nanometer squared into centimeters squared. Doesn't really matter, really, at the end of the day. Yeah, so let's convert let's convert nanometers into centimeters. So 0.015386 1 over nanometers squared. So the conversion here is going to be, let's see if I can do it. So 1 nanometer has how many centimeters? That's a good question. So it's 10 to the something. 10 to the... sorry. 1 centimeter has how many nanometers is the better way of doing it. So it's 10 to the 6. But how do we know 10 to the 6? Because nanometer is 10 to the negative 9, and centimeter is 10 to the negative 3, so the difference here is 6. That's why.
Yo, Adam.
10 to the negative 2. Yeah.
I'm not sure if you got the number right for AC.
Let's see.
Did you do 1 divided by 65 square? I'm getting a different number.
Okay, I'm going to type it in. And yeah, I got a different number. I don't know what I did, but I did something different.
Should be
yeah.
0.00. Okay, yeah, you got it.
Okay, good. There you go. Okay, yeah. So nanometer is 10 to the 9, centimeter is 10 to the negative 2, 10 to the negative 9, 10 to the negative 2. So 10 to the negative 2 divided by 10 to the negative 9 is equal to 10 to the 7. Yes. Thank you. So that's 10 to the 7. And then I need to do that again. 10 to the 7 nanometers per 1 centimeter. And then that cancels with all that. Okay, so finally, we have 0.0153846 times 10 to the 14. So we get that this is equal to 1. These numbers are too big. 1.538. Oh no, it's not too big. It's still big. 1.53846 times 10 to the 12 per centimeter squared.
The number. 1 point. It's 236 right now.
What? Oh, yeah. The number changed. I forgot. This number is not the same number. This number is 0.000236668. 0.000236668 times 10 to the 14 is still a big number, but 2.3668 times 10. Oh yeah, of course, times 10 to the 10. Okay, so that's how many area A's we can fit per centimeter squared. So now we know that, so then we need to figure out, that's how many we have per centimeter squared. We know that A usable, right? Okay, well, we want to figure out number of A's. So to figure that out, we find A usable times A count, right? Like the density. So it's going to be 0.202 centimeters squared times 2.3668 times 10 to the 10 per centimeter squared. And we get that this is times 0.202. So we get like a big number. Way too big.
Sorry, isn't it the 0.155, that one? 0.202 is before you calculate the usable area.
Oh, yeah. You're right. 0.155. Yeah. But no matter what, we're getting a number that's way too big. So, sorry, that number was right. This is 2.3. And this
Hold
is...
on. May I suggest something?
You may.
Because for the AC, like don't worry about the conversion rate. What you only need to do is like 1 over f squared, right?
Yeah.
Then just multiply that by 10 to the power of 6, and make sure the f is in nanometer unit. That's all. The rest.
But like, why? Like, what does that do? Like, you're saying it's in nanometers, and then multiply by 10 to the 6. So
Yeah. 10 to the 6. That's like outside the bracket. That's what he did in lecture.
And then what unit do you get after that? Like per millimeter squared, you get, right? You get the amount per millimeter squared.
Yeah.
Which should be the same. I mean, it doesn't matter. Like, yeah, if I do that, if I do 1 over 65 squared, and then I multiply that by 10 to the 6, it doesn't like it, times 10 to the 6. Okay, I get some number. But now I need to convert, this is in per millimeter squared, so I need to convert this into centimeter squared. So it's going to be millimeter, centimeter, right? Millimeter, centimeter. 1 centimeter has 10 millimeters. So it's times 100. Oh yeah, I get a different number. I get 23,000. Did we do something wrong here? One over 65.
Wait, no. So what after you use the formula, with the 10 to the 6, I believe the unit is in millimeter square.
Yeah.
So then just convert the A usable from centimeter square to millimeter square, right?
No, I get that, but shouldn't, like, what we're doing here should also work. I mean, I just convert to centimeter squared, right? Like, it doesn't need to be that. But this number is not working out properly, because this is 1 over 65 nanometers squared. So 1 over 65 squared is that. And then I have nanometer squared. And then we said 1 10 to the 7 nanometers. And this is 10 to the 7. 10 to the 7, so 10 to the 14. 10 to the 10. I don't know. I just, like, this should work. I understand what you're saying. Like, because what you get it in there. Well, would you even get it in that? Because you're saying I have, like, 1 over 65 nanometers squared times 10 to the 6. So what's that doing? So it's getting, like, on the bottom we have 10 to the negative 18, and then we have 10 to the 6 here, right?
Wait, Adam, try this. That nanometer thing,
Yeah.
because in the lecture note, what he did was the future size in micrometer, right?
Yeah.
That 10 to the power of 6 is responsible for, like, from micrometer back to the normal.
Yeah. Or no, that 10 to the 6 is getting from nanometer to micrometer, right?
No, that's a different thing. I believe that is from micro going to. What's this?
But we're not in micro. We're in nanometers.
No. Yeah, that 10 to the power of 6, I think that's from micro to millimeter.
But so then we shouldn't use it here, because we're not in micrometers here.
Yeah, we should convert 65 nano to 0.065.
Oh, you're saying
micro.
first turn that to micrometers and then do 10 to the 6.
Yeah.
Okay. So then, so let's say, just for the second, let's just say it's 65 micrometers, and then this is going to be 12, and then we have 10 to the 6, so then this is going to be 10 to the 18, 10 to the, the numbers still don't make sense to me here. because this is 1 over 10 to the negative 18. But that's a tiny number. That's like a way order of magnitude off of a... Or it's a huge number, actually. What am I saying? It's a huge number. I don't know. The units just aren't making sense to me. But let's just... I guess it's fine. Just whatever. So basically scrap all this because the units aren't making sense. I don't know. I still can't really figure out why the units aren't working out. But we essentially now just need to turn this into 1 over 60, 0 0.65, move the decimal place 3 spots, right? So 1, 2, 3, 0.065 micrometers squared. And then I'll put in a different color, times 10 to the 6.
Hold on.
We'll force
you either
the
do
units
one
to...
of those.
Oh, you don't. Never mind. So you...
Either or. So if you want to do a nanometer, you have to multiply it by 10 to the 6. If you do it in micro, don't even bother. Do you get what I'm saying?
I know what you're saying, but I don't understand how the units work out like that. That's the thing. Right? Okay, but let's just try it. So let's try what you're saying. So if I do 1 over 65 squared times 10 to the 6 10 to the 6, I get 236 per millimeter squared.
Yep.
And then if I do 0.065 to the negative 2, I get 236. Yeah, okay. I guess the units are working out. I don't know. Anyways, it's 236 per millimeter squared. So, yeah. Okay. So just convert it to micrometers, and then when you do it, it's going to be per millimeter squared. That's the thing to remember. Just convert it to micrometers. When you do it, it's going to be 236, whatever, 0.7 per millimeter squared. So that means you also have to convert this to millimeter squared, right? So that means just multiplying it by, I just have to do it here. Centimeters squared times millimeter.
Move it twice. Move it twice to the right.
1 centimeter. Yeah, 1 centimeter has 10 millimeters. So multiply by 100. There you go. Multiply by 100. So 1, 2. So 15.554 millimeters squared. Okay, so there we go. So that's making more sense now, because then we can do A usable is going to be 15.554 millimeters squared, and then this is 236.7 per millimeter squared. So we do 15.554 times 236.7. 3,681.82. Let's round it to 82. So that's how many usable number of these A units we have. 3,682. So now we need to figure out this, we basically need to figure out this remaining bit here, right? So this remaining bit here is just going to be all that minus the 1,000 at the end, or the 3,682 minus, and then just add all that together. 300 plus 150 plus 185 plus 250, 400 plus 1024. So we get, we get that the actual size of L2 cache is 1408A, which is how many gigabytes or kilobytes or whatever, not gigabytes. I keep saying gigabytes. So just like if you have n kilobytes, this corresponds to 4n A's. I don't really know why. This is just how it is. So if I have that many A's, then I just need to divide that by 4 to get the kilobytes. So it's going to be 1408 over 4 kilobytes. So I get 352 kilobytes. So that's the actual size. No, that's the actual size. Kind of weird wording, but that's the actual size. And then the practical size, it has to just be some kind of like, not power of 2, but a sum of powers of 2, right? So it has to be like 256 plus, well, you can try to add 64. 256 plus 64 is 320, so that's fine. And then you can try to add 32, which is 250. You can add 32, which is 352 kilobytes. So I think that's also the practical size, but you have to just make sure that it's like the sum of powers of 2. There we go. The units are the main thing that's confusing there, at least for me. Units are the main thing. But yeah, that's that. If anybody has any comments, please let me know. If there's anything else that's missing still, I don't think there is. Specify all component areas, we have that here. Well, like it's 1408A areas, right? This area, this unitless area A, right? So that 1408 came from, where did 1408 come from? 1408 came from, oh yeah, this number minus the sum of all other areas. Sum of all areas equals this, right? So that's like all these areas, right? So if the whole if we know the area of the whole chip and we know the area of all these pieces, then the only thing left is that. Okay, someone asked for question 1 from the sample, so let's do question 1 from the sample. So we're gonna have this question. So someone's asking about the units, how I convert it to millimeters. Yeah, so like yeah, that doesn't make sense. That doesn't make sense at all, but this matches how he did in the lecture.
I think it's just the unit of A is just like a really mysterious, weird thing. It says in the lecture, slide 27, A is defined as 1 millimeter square of die area when F is 1 micrometer.
Right.
So because our F is in nanometers, that's where that conversion of 10 to the 6 is coming from. You're converting from a micrometer to a nanometer and then squaring it.
Yeah. Okay.
So then I guess the final unit ends up being like A per millimeter squared, technically.
Yeah.
If you want to write it
I
that
guess
way.
so. And then the unit kind of works out because of that.
Yeah.
There's an A on the top.
I thought it was unitless because he didn't write it in, but yeah, I don't think it is. I think that's like technically the proper unit, but
it's just weird that we have like micrometer squared and then really nothing else. It just turns into millimeter squared. But that's how it is, I think. I think that's just how it is. You get millimeter squared. Okay, well, there's that. So let's keep moving because I don't have too much time. So an SOC has 6 tasks. Oops, why is it scrolling? T1, T2, T3, T4, T5, T6. Blah, blah, blah. Okay, sounds good. The SoC has a CPU, accelerator, dual port memory. The memory is used for sharing data between the accelerator and CPU, with the accelerator and CPU containing their own internal memories. Consider offloading and communication costs in the architecture where every bus transaction between the CPU and accelerator endures a 10 clock cycle latency. Apparently the clock is equal to 5 megahertz. Right? So that's something that's important. This is just like a separate thing that was, also this. He just mentioned this in the lecture. So that means that, T is equal to 1 over 5 times 10 to the 6, which is, 0.2 microseconds. Mega is 10 to the 6, right? Yeah. So, great. So 10 clock cycles is, is just going to be 2 microseconds. So that means that there is a 2 microsecond clock latency between the transaction between the CPU and the accelerator. Specific execution time for each blah, blah, blah. Assume no startup costs. Determine and clearly state the optimal task. Someone's saying, so you're saying the clock will always be 5 megahertz if not stated? I think it will be stated. But if it's not stated, then yeah, just say like assuming clock is whatever you want it to be. To be honest, at that point, if they don't say it, that's really a mistake on his part if he doesn't say it. So, and then just solve from there. So it says determine and clearly state the optimal task mapping for the DFG and scheduling diagram so that the SoC completes its task in the least amount of time as possible. Okay. So we have all of our different things here, right? We have our CPU, which can be working. We have our accelerator. So the confusing thing is the whole with the transaction times, right? That's kind of the confusing part of this. So, anyways, the first task is on is T1. T1 and T2 have to be completed before T3 can be completed. It takes 50 microseconds on the CPU. It takes 25 microseconds on the accelerator. But if we want to send it to the accelerator, we have to wait 2 microseconds. But I think that's fine. So we can send it to the accelerator. So we have to wait 2 microseconds. This is just like D for delay. So this is going to be, 2. It's all in microseconds. And then it'll take 25 seconds for task T1 to be completed. And this will finish at 27 microseconds. Then the CPU, I guess, in the meantime can be completing task T2, because it's really not that far after, right? T2, and it'll take more time to send it to the accelerator and all that. So task T2 can be completed here, and it'll be done at 40. No transaction time needed here. Now, if I'm wrong about something, please tell me. But here I'm. There's a delay before T1 because it told us in the question that every bus transaction between the CPU and the accelerator endures a 10 clock cycle latency, which is 2 microseconds. Anyway, so that's that. Then the next part is we have T3. T3 has to start now at 40. T3 is, on the accelerator in 10 or on the CPU in 20. I think it still makes sense to just send it to the accelerator. So there's a delay of 2, again, a delay of 2. So this is at 42 here. And then it will now complete its task for T3, and it'll be done by T3. It'll take 10 seconds, right? So it's going to be 52, or 10 microseconds. At 52, it'll be done. So for T1, since you are going to the accumulator, you have to delay. I think so. Yeah. Same with T3 here, right? T3, I'm going to the accumulator. So I have to delay a little bit. Then so at 52, we have the task T3 complete because it started at 42 on the accelerator. then task T4 has to be completed on the CPU. So I think we can just start it right away. Task T4. I'm going to run out of room, so, well, we're almost done, but let's draw a little smaller. So task T4 has to be completed on the CPU, and this will take 10 seconds. So this is going to be microseconds. So it's going to be at 62. It's going to be done. And task T5 has to be completed on the accelerator. Yeah.
T4 depends on T3. There's the clock delay between T3 and T4.
Yeah, so you think this should start at 54?
Yeah. Because the information from the accumulator has to get to the CPU before T4 can start.
So like there's an additional delay here, but it didn't matter. Like for this year.
No, that one doesn't need to, since T3 is on the accumulator anyways. Because T1.
Oh, so it doesn't need to send it doesn't need to send the information back?
Yeah. There's only a delay when it sends it between the CPU and the accumulator, or the accelerator, not accumulator.
Okay. Does this match with what he did in the lecture?
Yeah. Well, that's what he did during the example.
Yeah.
Actually.
I'm pretty sure, from what I can tell, like, because he didn't include, like, he only accounts for it once, is because that 10 cycle accounts for both, like, round trip. That's why he didn't include it. So like that 10 is already like, yeah.
Let's see here. Yeah. We'll verify this. Okay, so T1, T2. Then, oh no, sorry. This is without. This is with it. Yeah, 2 microseconds. So at the end of T2, so at the end of T1, I mean, sorry, that's on the accelerator, it sends the information back, and so there's a delay there at the end of T1. And then here at time, so this is still on the CPU, but anyways, here T5 is starting. T5 needs the value of T3, so you need to communicate the value of T3 to the accelerator to do T5, so it needs that information there. So it needs a delay of 2. And then T4 is done on the CPU. Okay. And I'm assuming that's supposed to be T6 right there. T6 is done on the accelerator, so it needs to communicate the information, the result of T4. T5's already there, but T4 has to go as well. Only thing that's weird is like, why is this? Oh yeah, T1 is here because T3 is computed on the CPU. So that's why it needs to be sent back. And at the end, our result is on the accumulator. And I'm assuming that's fine. So technically it should end at 89 because the result of the accumulator should be sent back to the CPU. But he didn't include that, so whatever. But yeah, whenever it necessarily switches. So right now T1 is on, T1 and T2 don't require any previous information, so it doesn't really matter. But T1 is being sent to the accumulator. Okay, but there's no delay at the start. There's no starting delay. So T1 is just done at 25, according to him. T1, that's an important point. T1 is just done at 25. It's only...
But now the thing is, like, how does the accelerator knows what kind of thing it's like when is it active? You know what I'm saying?
Actually, I guess it does. It doesn't.
Device.
But it doesn't need any input data. It doesn't need any input data. So it's just a signal. But the transfer of data is what causes the delay, not just the fact that it's activated.
When does it activate? That's the problem, Like,
yeah,
does it always on idle? But like there should be like there's a flag that is like, oh, you got to do some work.
Yeah.
But apparently
I think that makes sense.
But
though.
then
T1, and then this finishes at 25. It doesn't finish 27 because it doesn't need any input data from the CPU. It just starts working. Oh no, but how would it just start working? I don't know.
You see, that's my point.
How would it just start working
right?
without input data?
Like, how does it even right? There should be something in the negative, like saying that you should go to work.
Or there just has to be data for it to work on. Like it can't just work off of no data.
Exactly. So that's from what? From where? The CPU.
From the CPU.
Right?
Well, I'm assuming this this chart is supposed to be for when the program actually starts. And everything before, the CPU would like set up everything,
Okay.
and then like it starts the program, and then this chart
Yeah.
shows like what happens after it starts.
Yeah. I agree that probably there's just stuff before this that happened. And let's say T1 let's just say T1 takes no input. However that would work, I don't know. T1 takes no input. So T1 can just activate and it'll be done by 25. There's no data that needs to be transferred there. Yeah, maybe write an assumption. Yeah. I agree that we should just follow what the prof did there, just to maintain marks here. T1 ends at 25. T2 ends at 40. T3, which requires information from T2, therefore we need a delay here, will start at 42 and end at 52. T3 will send information to T4, which is being completed, so there needs to be a delay here. Because T4 is going to be completed on the CPU, but T4 needs the result of T3, and so data needs to be communicated again to 54, and then this is going to be T4 here, which is on the CPU, and will end at 64. I know what you're saying, right? So someone's saying in the chat, for the professor example, it says T1 ends at 25, but it says T1 to T3 on the bus line. So I think that would mean it does end at 27, but in the perspective of the accelerator, it ends at 25. So I agree, but but I think that there also like is no, did I include that here? Yeah. But that's, but that's only because T3 was being done on the CPU there. I didn't do T3 on the CPU. I did T3 on the accelerator, which is faster than what he did, right? T3 it's still smaller. It's 14 here. Anyways, so yeah, there can be multiple solutions. Okay, sounds good. Anyway, so the data is transferred. I should have like another thing here that's like bus, like how he did it like above, right? It's not really associated with this, but anyways. So T3 is finishing. T3 finishes and sends the data to T4. T5 also needs to be running, right? But T5 can just be running. Okay, so when can T5 start? T5 needs the result of T3 already on the accelerator. Great. So can T5 just start like at the same time? So why don't I put this D here? And why don't I put this D here? So do you think T5 can just start like here? Because T5 has to be on the accelerator. T5 also needs the result of T3 already on the accelerator. So then it's just 5 seconds. So it's going to end at 57. And then we'd probably transfer the result of T4. So we need another data here, which will be at 66 microseconds. And then this will take another 15 here for T6, which will finish at 66 plus 15, right? So 66 plus 15 is 81 microseconds. Did that end up being faster than his? Yeah, he said 87. Now, the only thing that I'm not 100% sure about, I mean, the whole thing, but the thing that I'm worriedly not sure about is, can T5 just activate like right there? Or does it have to wait until the delay finishes?
That should be fine. I don't see any problem with it.
Okay.
Because they do that in his example. He does that with like the T3 to T4. When T3 is transferring to T5, T4 starts running.
Like here, when T5, but T5 starts running after a 2-second delay.
Yeah, but T4 starts running immediately.
Oh yeah, but T4 starts running immediately. Yes, T4 starts running immediately. Yeah. I see what you're saying. Yeah, I agree. Okay, so it looks like that all these components can communicate and also compute at the same time. Okay, well, that's my answer. Hopefully we get a similar question. Yeah, okay. Yeah, so you only add delay when switching between CPU and accelerator. Exactly, when a piece of data needs to move from the CPU to the accelerator, or the accelerator to the CPU. And only when it needs to. It doesn't just always do it, right? Only when a following task requires information. Okay, so there's that question done. Well, I'm gonna probably wrap up in like 5-10 minutes because I'm still downtown. I gotta get home. And then I gotta get back. I gotta get some sleep. But 5-10 minutes here. Anything else you guys want to talk about? Because the rest of it, like, those are probably, like, definitely we're gonna get a question like this. Definitely we're gonna get a question like this. And then we're gonna get a System C question, but System C question is not too hard. It's just kind of, you know, see your system, whatever. Anyways, it's just kind of like example like this. Using the notes. Here I'm getting a message. 2016 exam. Okay, let's see this. Oh yeah, from the 2016 exam. SoC, same thing. Shown in the figure, displays two architectures. Okay, well, let's just do it. Oh, two accelerators. And dual port memory. The memory is used for sharing data between the accelerators and CPU, with each accelerator and CPU containing their own tangent memories. Consider offloading communication costs. Again, 10 clock cycles. Specific execution times for each core is given. Assume no startup costs. Pretty much the exact same thing. Still, I'm assuming. Well, here it said one. Let's just stick with our assumption that it's two clock cycles, or 2 microseconds. Is what I'm trying to say. So if it's 2 microseconds, okay, let's do it. So again, I'll draw out this little graph. Boom, boom, boom. Boom, 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 boom. So I'll have separately CPU, call it bus, and then 2 accelerators, right? Accelerator. So accelerator 1, accelerator 2. So, okay. So task 1 needs to complete before anything else can process. So probably it makes sense to do it on the fastest possible one. Again, accelerator 1 doesn't take in any information, so we should just, task 1, I can't speak. Task 1 doesn't take in any information, so we may as well just start it here, and it'll complete in 20 microseconds. Now that task 1 is complete, we can start task 2 or task 3. Task 2 requires T1, so it'd be nice to keep it on here, but it doesn't really matter. So I'm assuming also the communication between, so every bus transaction between CPU and accelerator endures a 10 clock cycle latency. But what about accelerator to accelerator? Because what if I want to take the information from T1 and put it on accelerator 1? I'm going to assume that also takes 2 microseconds. So now we're going to put that here for task T2. T2 is going to start at 22. Again, I'm assuming that like 10 clock cycles is 2 microseconds here. So T2 is then going to finish at T2 on the accelerator 1 is 15. So 22 plus 15 is 37. Like that. So then, okay, interesting. Yeah, this is the solution. Someone sent the solution here. Okay, I don't know. Let's just try it like this and see if we get a better answer. So I'm switching to accelerator 1. Oh yeah, because then task 3. Oh, task 3 has to be completed on accelerator 1. I didn't see that. Or a CPU. But okay, so this actually doesn't make sense because I thought we were going to be able to do task 3 on maybe the other accelerator or something. But yeah, okay, that makes sense. So task 3 has to be completed here. So we may as well just start task 3. Right? Task 3, which can be completed here, right, happens in 10. So T3, this is going to finish at 30 here. In the meantime, right, accelerator 1 can get the information. So delay spot there, right? This is at 22. And then task 2 can be completed using accelerator 1. Accelerator 1 being 15 microseconds, right?
Adam,
Yes.
I believe T3 cannot be done on AC2.
Oh, sorry. Yeah. My bad. Okay. Task 3 cannot be done on AC. Yes. So task 3, okay, so this still needs this communication. And so task 3 has to be completed here. T3, and it'll be done at 32. Task 2 can be done on accelerator 2, and it'll take 20. So we may as well just do that. So task T2, and it'll be done at 40. So now at this point, we just have to do, well, when T3 finishes, T5 could start, and T5 has to be done on the CPU. So we need to communicate the value of T3 to the CPU. The CPU will start executing at 34, and it will complete task T5 once T3 is done, and it will be finished at 44. Only thing left is T4. So T4 can start once T2 is complete, which is at 40. T4 can be done on accelerator 2. In fact, it's the fastest on accelerator 2. So that's exactly what we should do. We should put it here, and we should put T4 right here. And T4 will be done 15 microseconds after 40, so at 55. So there we go. And is that exactly the same thing like what the solution manual is? Or the solution? It is, but the number doesn't match up. T5. Okay, I don't know. Anyways, there can be multiple solutions, so. Okay, that's my answer. I think this makes sense. T1, then T3 has to be done on accelerator 1. Yeah, -2 marks for no DFG map. I do not know what that means. Like maybe on the DFG here, you see here how they said like accelerator 1, accelerator 2, but then they didn't put what's on the other stuff. They didn't say like, well, first of all, it doesn't matter. It doesn't make sense to say accelerator 1, accelerator 2. So it's accelerator 1. So maybe you have to label on the DFG like what components are doing what. I don't know. Okay, guys. Well, that's probably our time for today. I got to get home. and finish up for the day. So I'll stop recording.